All right, thank you all. Thanks for coming this morning, and thanks for having me. I feel a little bit unprepared because I don't have nearly as many incriminating pictures of Nico as he had of me in my talk, so I'm a little upset with myself about that. So I want to get through this quick. There's a lot of information to go through for everybody, but I always like to start off with some acknowledgments. There's just an amazing number of people working on ABCD. A lot of the things that have been going on here have been put together by the DIAC of ABCD and Anders Dale, BJ Casey, Don Hagler, and lots of other folks that put all this stuff together. I also have some data in here with collaborators that include Nico and Steve and a really amazing group of people from my lab that have been contributing to a lot of this stuff. In particular, Derek Sturgeon, who you can see up here, helped develop some of the pipelines we're going to talk about real briefly. And he has a poster on Thursday, and so if you want to see more about this, you feel free to go see that. All right, so there's three goals. One is I'll just talk quickly about the characteristics of what we call the ABCD HCP BIDS app. I'll go over some early benchmarks of the connectivity data to show the reliability of these data, and then we'll talk about personalized connectivity networks in ABCD of the similar vein of what Nico was just talking about. Okay, so first is the BIDS app, the ABCD HCP BIDS app. It's containerized software. It has standardized inputs. It's really minimalistic, and so it's really easy to use. It's in a Docker container, so it uses lots of different software packages, but because they're all pre-installed, it makes it really easy for users to use it just in general. For folks who don't know about the BIDS standards, it requires a BIDS inputs, which is related to, it's called the brain imaging data structure. That's a really standardized format for how the data is organized and the metadata is organized. There's a nice app that we have now that we call an ABCD DICOM to BIDS that's available on the GitHub page that allows people to essentially download the raw data from the NDA and then turn it into BIDS format for your own use if you want. But at the same time, as you'll see here, is that all the BIDS data from ABCD is being uploaded to NDA as we speak, and I'll talk a little bit more about that shortly. So again, this new app, right, is really minimalistic. All it takes is Docker, knowing the path to your BIDS input and where you want to process the data, and then really one command line argument, and then essentially you're done. There's lots of different kind of flags and stuff you might want to put in there, but that's really just how it works. For those of you that have used the human connectome pipelines, there's a few differences. One is that here it will just detect what kind of configuration you have in your data. So if you have just a T1, or you have T1 and T2, if you have T1 and T2 plus the field map, it just detects what you have, and then it will just run the appropriate thing. There's some modifications to the human connectome pipelines with regard to FreeSurfer and pre and post FreeSurfer to kind of improve the performance on different data types. Allows for different templates to be added if you want, and there's a new functional connectivity processing module, some things that we deal with filtering respiratory artifacts, and there's also a quality control module. So it works with ABCD data, it works with legacy non-ABCD data acquisition, and it works with specialized populations. So for example, like even the data that Nico was showing earlier, is if you have subjects like aging populations with big ventricles and things like that, there's a module to help you kind of get them into space and analyze them and compare them to normalized data sets. This is just one example. It also spits out some QC information. So these are gray plots, which allows you to see kind of the quality of your data before and after you've done your pre-processing. These data are really nice because you'll be amazed that once you start looking at your data, all the junk that's in your data, even after you've thought you've cleaned it all out. So these just visualizations really allow for making sure the data quality is really strong for all the papers that you want to put through. And then it also just kind of makes a web page that makes it really easy to go through how well your surfaces are made and how good the registrations are, and all of that really easily in a nice little web page at the very end that we're calling the executive summary. And the last is that it can spit out what's called BIDS derivatives, which are the standards for BIDS is not complete with the derivatives, but there's some standardized outputs too, so that if you're building apps on top of the outputs, then it's more easily applied to other people's data. Okay, so again, there's a couple of repositories, one for my lab, the DCAN labs, and also the ABCD study where you can get all this information and kind of repeat some of the things I've been talking about today if you'd like. So this app is actually available now. You can go down and download it if you'd like. The BIDS input data for all ABCD subjects is being uploaded, like I said, right now, as well as the process data from this app. And it will be available next month in July for people to download from the NDA. So this has been a massive effort. So again, like 11,000, you can see nearly 12,000 people have been scanned for ABCD. About 11,000 unique subjects have data that's been uploaded to the AWS Fast Track, which you can have access to, and about just slightly under that have at least good T1 images that can go through this app, and all that stuff is going to be available very shortly for people to go crazy on. All right, so there's some brief benchmarks on the ABC data. This data is actually from a paper that's under revision right now with Scott Merrick and Nico's lab, where what we've done is we've kind of stratified the data set for ABCD into two split halves, so like approximately 5,500 subjects per half, so you can have a discovery and replication data set that's matched perfectly across all the demographics and familiarity and things like that. And then what Scott did is he took a subset of that data and just ran a really easy connectivity matrix based on the Gordon parcellation, which you can see on the left, which is called the discovery data set. And then he ran it again on the replication data set, which is completely independent people, about 1,000 subjects. And then what you can do is you can compare those two matrices to see how replicable your data is based on what we've done to all the data, right? And the nice thing about this is that the correlation between those two matrices that are completely independent is 0.99, meaning they're nearly identical, which suggests that these data, the quality is really strong and will allow for very nice things to be examined against depending on your level of interest. The same general result can be seen for the connectomes or the network organization, which is in B, suggesting that the data again is really strong and it's going to be very nice for making sure that a lot of the work that we're doing is actually reliable. There are a few things that people have to be noticed about. So one is there's site differences. So this is just a map of every, the matrices of every subject relative to every other subject. And what you can see in this map is that there are some sites and some data that are, depending on the scanner manufacturer, they're slightly different. I mean, the difference is minimal, but they're still there. So it's things you got to think about when you're running your analysis with ABCD. All right. So the conclusion here is the data look good, they're reliable, there are some scanner differences, so you got to think about that, as well as a few other things. But we're excited to have these data in people's hands to kind of go crazy. All right. So last bit here, what I'm going to talk about is based as a riff off Nico's talk. People kind of recognize what graph theory is, where we're just trying to take a bunch of nodes connected by edges. In our case, the nodes are vertices in the brain, and the edges are this connectivity matrix. We can apply techniques like community detection, like what Nico was showing, to identify specific brain networks and systems. This has been done for many years. In fact, we take it kind of for granted now with regard to how these networks were originally defined by across lots of different labs and different folks. But again, in general, right, is what happens is we look at this as across a group average. And what Nico was just describing is like, well, what happens if we actually look at individuals? In this case, scanning 10 people, right? 5 hours long. So the idea, right, is that you want to figure out, right, what's specific about this individual, right? Nobody's average, right? There's some people are above average, and there's several people that are below. We want to figure that out. So what Nico just showed is like if you look at these individual networks, there's lots of these very specific differences that you can see in them based on their network organization. The problem is, and again, what he showed the figure on the right, and this is based on the Poldrome data, is that you need lots and lots and lots and lots of data, right, to be able to get this individual system, right? And so not surprisingly, at the beginning of ABCD, I was like, well, I feel like we need at least 400 minutes all 12,000 kids every year for 10 years, just to be able to really look at this out, right? And unfortunately, I was voted down on that proposal, and so we kind of were left with this. What we're doing now, which is 4 5-minute runs, about 20 minutes of data per subject, that we can, with the hope that we can get at least 10 to 12 minutes of movement-free data per subject. The reason is because if you look at that graph, the very left-hand portion is the 10-minute mark, and then just above that, as you can see, it rises quickly. You can get about a relationship between systems about 0.9 or 0.8 if we have, upwards of between 15 and 20 minutes of data. The good news is if you have lots of data for the best subjects in ABCD, you can run the identical analyses that Nico did on those 10 subjects, and you can get a lot of systems that come out that look very similar to what you see in those subjects who have hours of data. Okay, so the data quality is good. You can see some of these things. The problem with that is that you need subjects. It only really works with subjects with more than 17 minutes of data. Now, if you look at the motion qualities of ABCD, this is a picture of that. On the left hand is you have the frame displacement, where your cutoffs are for too bad of movement data. On the bottom you have the number of minutes that you get for a given subject at that time frame. And the color is how many subjects in ABCD. This is a relative example of about 1,000 subjects. How many subjects are available at that cutoff for this amount of good data? And if you go up to 17 minutes, where that blue cutoff is, I'm putting the yellow arrow there. You're for every 1,000 subjects, you're about around 300 subjects hit that 17 mark, which is not a great percentage, right? And so we're not going to be able to really utilize the full data set for this kind of purpose if you need more than 17 minutes of data. So one of the things that we've been playing with is using this technique that Evan published in Cerebral Cortex, or a variation of this technique, where you can do the same type of network identification, but slightly different, where instead of using community detection, which is kind of unsupervised, you do a supervised approach where you first take a seed region, which is on the left, this vertex map, you binarize it, and then you compare it to your template or your average, okay? And then you say, well, that seed region, whichever network it looks most like, you kind of label it, which is on the bottom, number 4. You label it as that network. If you go through all the vertices, you can figure out, you can kind of get a personalized system organization, just like you do with community detection, but in a supervised way, and presumably would take less data. So we've been testing this a little bit with the MSC data, the same data Nico was talking about. What we've done is we've taken those subjects and we split all the data for every subject into 2 halves. So each half has about 2 hours of data, or just over 2 hours of data or so. And then from that, this is just an example of 2 of those subjects across their split halves. From that, we can say, if we did this technique now with this identifying these individual communities based on this technique, they should look the same across the 2 halves. If we, in the same way that we can see with the other InfoMap or typical community detection algorithms. We can compare that using what's called mutual information. And when you do that across all the subjects in the MST data, what you can see is that if you compare what the connectomes look like between people within themselves, like what one half looks like to the other half compared to kind of the other participants, is that the distributions are completely separate, suggesting that the technique at the base level is giving you systems that are indeed very unique per person. There's one other figure, unfortunately I don't have here today, but it shows that the variation you get from this technique compared to using InfoMap, which requires a lot more data, is relatively similar. Now, there's some more work to do on that, but we're kind of moving towards validating this might be a good approach that could be used for ABCD. The next question is like, well, how much data do you actually need to be able to reach that plateau, right? And so here, now what we're doing is we're saying we're taking one half, we're using it as the baseline, and then we're taking the other half, and now we can kind of take out 5 minutes of data, 10 minutes of data, 20 minutes of data, and so forth, right? And then compare it in the same way using mutual information, which will give us how soon can we get to the networks to be somewhat similar. So here's the picture of that on the right, and what you can see is that the curve, as you increase the amount of minutes per data, the curve kind of increases very quickly on a per subject basis with MSC data. By about 10 minutes, you're starting to see some plateau. They're still rising, but you can see somewhere between 10 and 15 minutes, you can see it starts to flatten a little bit, at least with regard to these networks. So we're kind of in the range of what we're collecting for ABCD and what we anticipated we'd have, which is between 10 and 12 minutes of good data per subject across everybody. So the last question here is, well, how might we examine the robustness of this technique in ABCD? Well, because we don't have the same type of split half data analysis that we can do like you can do with MSC. Well, one thing that we decided to try is we said, well, we have a lot of twin data, right? Monozygotic twin data that exists in ABCD. And we can look at the individual network characteristics between monozygotic twins, and based on some prior literature, we would expect that they would be more similar between each other than unrelated participants, and that should give us a little bit of an idea that maybe this system will work. So that's exactly what we did. In this case, now we're, instead of looking at split halves, we're looking at twin 1 versus twin 2. And if you stare at these things a lot, like I have, it's really fascinating where you can start seeing like these very, very, very specific changes that you would always, in the past, I thought was just noise in the data that are actually present across twins. So this is one example where you have the ventral tension system that kind of is roping up along the, into the frontoparietal system. There's examples of the other examples of single percolor system. We have very specific things between the twins. These very, very, very unique aspects of the data that seem to be present across twins. So that's just the eye test, but of course we can quantify that using the same mutual information by comparing twin 1 versus twin 2 versus unrelated people. And if you do that, this is the distributions of ABCD. This is only of 32 twins. There's more, and there's lots of dizygotic twins that I'm not going to have time to show you the data. But you can see that the distributions of these individualized networks are starting to separate, which is telling us that what we're doing for these personalized networks is potentially working. Now we've also validated this further using the human connectome data, which also has monozygotic twins. And again, a lot of the same findings that you can see in the ABCD data are present in adults in the HCP data, suggesting that we're kind of moving towards in the right direction. So to conclude here is that the ABCD data is strong and reliable. Traditional approaches to this individual network identification might be difficult and this many subjects because of how it's being done, but it is possible with these other techniques that identify individual networks. Still a little more work to do, but we feel good based on some of the data that we've seen so far. So coming soon, again, like the first wave of these BIDS data and the derivatives, like they're coming out in July of next month. We have a second wave of data that will include task outputs and a few other things. DTI is coming. It's going to be a little bit longer. We have a little bit further validation to do, but then we're going to release all these individualized networks across every single subject for people to kind of go crazy with, because there's lots of applications. And importantly, we want to work with the community to kind of about needs and wants of what folks want to be doing with the data, so we can kind of standardize how we want to release some of these kind of data and inputs and outputs for folks to use. Thank you all for coming, and thanks to the lab and of course all the funding. Thanks.